In this video, we're going to look at how to write the equations of the graphs of the sine and cosine function. And notice I do have both of them because, as we've talked about, any sine function can also be represented as a cosine function and vice versa because they're just looking at the same thing. They're just looking from two different perspectives within a right triangle. So we're just going to jump right into the examples here. Here I have a picture of clearly a sine or cosine wave, sine and cosine wave in fact. And what I want to do is I want to write out what that equation will be. Now, there is usually an easier way to write these between sine and cosine. There's usually an easier choice. But before I get to any of that, it doesn't matter if I'm looking at a sine or cosine. There are two elements that will be consistent throughout, and that will be the amplitude and the period. So I'm going to start by finding the amplitude, and then we'll find the period, and we'll think about how that helps me with the equation. So the amplitude, remember, is how tall is this wave? And not from the bottom to the top, but kind of from that level watermark, what I call the still water or flat watermark till the top of the wave. And we can see that's clearly 2. It should be the same distance from that level watermark to the bottom of the wave, also 2. So the amplitude is 2, and remember that is equal to the a of the equation. It doesn't matter if we're using sine or cosine, we have that a sine bx plus c plus d equation, and of course could have a plus or minus on the a and b. So the a we already know is 2, and it doesn't matter if it's sine or cosine. Next thing I want to do is figure out the period. Well, the period is how long it takes to complete one wave. So for me, the easiest spot to look to and from would be from 0. It's always easiest to count off 0, and 0 also gives me a very distinct mark. If this wave had been shifted a little bit to where maybe this is, just some kind of random point in the wave, maybe it's not as easy to look at 0. But 0 starts at the max. So I'm going to look for that next max, and I see that's over here at 2 pi over 3. So that means my period is exactly 2 pi over 3. Now, did I have to look from max to max? No, I could have looked from min to min. If we look from negative pi over 3 to pi over 3, well, how far is that? Still 2 pi over 3. If I look from 0 to 0, now if I'm looking from 0 to 0, I have to be a little bit more careful. From 0 to 0, I can't just look to the very next 0 because that's not a full wave, right? We've only gone up. We haven't finished the down. So if I'm saying from 0 to 0, I have to make sure that the 0 is trending in the same direction. So the 0 on the incline, I need to go to the next 0 on the incline, so I'd be going from here, pi over 6, negative pi over 6, to a, basic math here, 3 pi over 6, and that gives us 4 pi over 6, or 2 pi over 3. And so any which way we look at it, we get the period of 2 pi over 3. That period is equal to 2 pi over b. These formulas are the same things we used when we were graphing the sines and cosines ourselves. We're just taking in the opposite direction this time. So right away we can see that b is supposed to be 3. But if we were to solve this, we could multiply the b over to the other side, divide off the 2 pi over 3, or that's the same as multiplying by the reciprocal. So the 2 pi's cancel. So like I said, we get b to be equal to 3. That one pretty easy from the first equation. So we have our a, we have our b. We need to figure out, is there any sort of phase shift? Is there any vertical shift, any reflections? Now the vertical shift will actually also be universally the same between sine and cosine. And here we can see this wave is completely balanced along the line y is equal to 0. So that is telling us the d is 0, there's no vertical shift. But if we want to talk about the c, and if we want to talk about the signs of the a and b, meaning the reflections, we do need to first define whether we're going to look at a sine or a cosine. So this brings me to, let's start with the easiest one. Now there's going to be a lot of cases where I ask you to do both because I want to see that we can do both. It's just a process. But if I look here, the easiest way to define this would be clearly through the cosine. Why do I say that it's cosine? Because cosine always starts at the maximum. So the cosine will be the easier version of this wave to write. Cosine starts at the maximum, so we don't need to have any sort of reflection or phase shift here. And therefore, we're just going to write very directly y is equal to 2, which was our a, cosine 3x. And that's a completely true equation. That equation gives us this wave right here. Let's, for the practice of it, also find an equation of sine. that would give us the same wave. Well, now here's where it's going to take a little bit more thought, because sine doesn't start at max. Sine starts at a 0. So I have several different zeros I can choose from. I would think it's easiest to start at the 0 that's increasing, because remember, sine typically increases and then decreases. Could we have started here? Absolutely, and in a few minutes we're going to see how we can do that. But I would choose the one where the sine is increasing. So if I start right here, let's think about what that phase shift was. This phase shift would be negative pi over 6, halfway to the negative pi over 3, negative pi over 6. I know that the phase shift is negative c over b, or remember, some books will call this c the opposite of c, and so you don't have to bring the negative in here, you do it when you do it in the equation. Anyway, which way? We need to make sure it's the opposite sign of the direction we went, so when we bring it into our equation, it's going to be a plus. So I need to solve this for c. I'm going to multiply the negative 3 to the other side, so c would be equal to negative pi over 2. And so now we can write the equation of the sine graph. Y is equal to, the a is still 2, sine, the b is still 3, that's not going to change, but what we are going to change is we're going to pull a negative pi over 2 into our equation. Remember, with the cofunction identities, the sine and the cosine are always off by a pi over 2. Now, where that pi over 2, which direction it takes us is dependent on which way the graph is pointed. So if we're writing a sine as a cosine, we should always see that the c values are off by pi over 2. In this case, we had a c of 0, this one pi over 2, and we've shifted to the left, and so that's a good indication I have my sign wrong. I made a simple mistake here. I said we need to be multiplying by a negative 3. It should give us a positive pi over 2. Always do a quick double check, make sure you have it going the right direction. We know if we go to the left, it should be a positive. Going to the right should give us a negative. Let's do this again, but this time I'm going to call this my phase shift, because sine just starts from a0. It doesn't have to be going up first. We can treat it as a reflection with a phase shift. So here the phase shift was a positive pi over 6. And so this time when I solve for the c, I will really get the negative pi over 2. But what we also said on this version is because it's going down first, we have to use a reflection. We're going to reflect over the x. So we could also write this as y is equal to negative 2 to get the reflection, sine 3x plus pi over 2. Notice in all three equations that we've written now, the a and the b are the same, the c is different, and potentially a reflection is different. I could do this all day long, right? I could have called this point right here my phase shift for sine. That would be negative, what did I say it was before? 3 pi over 6, 3 pi over 6 or pi over 2, right? And we could use that as our phase shift. We could have used this point over here as our phase shift with a reflection. So there's an infinite number of ways to write these sine graphs, and that is because the phase shift isn't strictly a horizontal shift anymore. It is a form of a horizontal shift, but because these waves are infinite, we're just kind of choosing where the phase starts. Where does this sequence of wave start? And so we have an infinite number of points to choose to start from. Now, that means cosine also has an infinite number of points to start from. Easiest thing to do is absolutely to say it starts on the y-axis, because that's where cosine typically passes through. But what if I'd thought about it starting over here at 2 pi over 3? I could have used a phase shift of 2 pi over 3, and I would have had a c term then. I don't need to do that, it makes it more complex, but I could have, right? And I'm saying start, but remember there's no start or end point to a sine or cosine wave. They're infinite waves. We're just choosing a point along the way to graph as that first point and representing the rest of the wave around it. I could have also chosen start at the minimum, and let's write out this equation just so we could see how this one works. So we see here we have a phase shift of pi over 3, and I know that the phase shift is equal to the negative c over b, and we already found the b to be 3, negative pi over 3, negative c over 3, sorry, getting ahead of myself. So very clearly my answer is going to be c is equal to a negative pi. Squeeze that in on top of the other graph. And so what we could also do is we could write this as y is equal to, starts at the bottom, so it's going to have a reflection, negative 2 cosine 3x minus pi. and that minus, of course, makes it move to the right, and so that would be another version. Why couldn't I have moved negative pi over 3 with the reflection? Well, I could have done that too. So just like with the sine, infinite number of solutions there. I think definitely the two in the black boxes are the easiest ones to get to, the cosine being the easiest by far. But we can represent these sines and cosines any number of ways. Let's take another example. Just clear that out so I have a little more room to work. Right, so this wave starts above the x-axis entirely, and so here we are going to have some sort of vertical shift we're going to have to implement. But let's start with the basics again. Let's start with the easy stuff. I'm going to start with my amplitude and my period. So the amplitude, remember, is not from the bottom of the wave to the top of the wave, but from where that flat watermark would be when there's no waves in the sea. Where is that level tide mark? So I'm going to put that as a dotted line through my graph to represent that is where the x-axis usually is on the sine and the cosine. Of course, here it's been shifted. So what we can see is from that halfway point up or down, there is 1 unit in distance. So that 1 is my A. The period. I'm going to count again from the y-axis because it seems like the easiest place to count from 0. So here I'm starting at 0. I'm making my way down first, so I hit another 0 here, and then I make my way up. So this would be the end of the wave, and we can see that distance there is 2 pi over 5. Now I was reading that as 0, but of course it's not. The y value there is 1, but I'm treating that dotted line, just for right now, I'm thinking of that dotted line as my old x-axis. And so the old 0 to this sine or cosine graph would have been right here, and then it repeats itself down here. We could have looked from the max to the max. Now the challenge in that is we don't have that mark denoted, but we could easily find its halfway point would be 3 pi over 10. We could have looked from min to min, same problem. We don't have those halfway marks denoted, but we could have. And then we could have subtracted the two values. Just seems like more work than what I need to do. The period will be 2 pi over 5. And the period is equal to 2 pi over b. And so when we solve this for b, we get b to be equal to 5, or b is 5. And the other thing that will be consistent between sine and cosine is a vertical shift. And clearly we can see here we have gone up 1. That old x-axis where the wave is kind of cut in half, that level water mark is at 1. So what that's telling me is the d term is equal to 1. Now from here, I need to decide if I'm going to use the sine or the cosine, and we're going to do both for the practice. So I'm going to start with the easier one. Which trig function typically passes through the 0 on the y-axis? I always am thinking about what happens on the y-axis. Well, typically at the 0 we see sine, and so the sine is going to be the easier function here. If we use the sine function, there is no phase shift. But it's not that there's nothing else happening, because sine we typically expect to go up first. It's going down first. And so what that tells us is we have a reflection. So let's build all of that into our wave. Y is equal to, it is an equation, so it needs to be y is equal to. Y is equal to, the amplitude was just 1, but we had that reflection. The b was 5x, and there's no phase shift, but there was a vertical shift up 1, so I'm going to have that plus 1 there. Now, just like before, you might be saying, well, shouldn't it go up first? Well, it could, right? We could have used a phase shift of negative pi over 5, and then we wouldn't have to use a reflection. Negative pi over 5 is equal to negative c over b. The b was equal to 5, so our c would be equal to pi. So we could have also written this as y is equal to sine 5x plus pi minus 1. That would have also worked. We don't have the reflection now because we've fixed the wrong direction, so to speak, by implementing a phase shift. Of course, we could have moved it to the right. We could have moved it over further and had another reflection. Any number of things we could do. Cosine. Let's work on the cosine next. Cosine typically starts at the max. So I'm going to find one of the maxes. There's 2 of them. Doesn't matter. I'm going to choose this one right here. And so what I see here is a phase shift of halfway to pi over 5 is pi over 10. The phase shift is equal to negative c over b. The b would be 10. And so we could write this as y is equal to, the amplitude is still 1, so I'm going to just have one cosine or cosine. The b is still 5. I said 10, and of course that's very wrong. It should be pi. Try that again. Let's back up. Sorry about that. Just mathematical breakdown. So if we are going to plug in our b, which I need to do, I'd have negative c over 5, and then when I solve that for c, the negatives cancel, but I'd have pi over 2. And so what I saw just a second ago is I was saying my c was 10. I just told you in the last example that the c should always be related to a pi over 2, the difference between sine and cosine, so I knew something was wrong. And now we have it correct. I just, for whatever reason, didn't find the c. And so we have y is equal to, the cosine has an amplitude of 1, so there's a 1 in front. The b is still 5. Our phase shift caused by the c value of pi over 2, we still have a vertical shift up by 1. Just noticing now too, in this red, this should have been a plus 1. Part of it is just I can't read my writing and my pen's not writing very clearly here. And so there would be our wave. We have the b brought in, we have our phase shift, the c brought in, and then we have the d brought in. Keep in mind, the c is not the phase shift, the b is not the period, but they are how we get to them, right? And so we have to use those equations the same way we wanted to use them to find the period in the phase shift. Once we know the period in the phase shift, we can get back to the c and the b by using those equations. I could have started the cosine at the minimum. I would have used a reflection. I would have used a phase shift there as well. And so, like we saw with the last example, there are any number of ways that we could write these sine and cosine functions.